Right, welcome to this presentation, Unit 3, Making Use of Energy. Still applicable for both physics and double award. Really, I would call this unit heat transfer. Shoehorned in here a little bit in amongst all the other electricity bit, but it does give us a good chance to talk about some domestic stuff and some other bits and pieces which are quite vital. Okay, so our objectives. Number one, density. We're going to introduce what density is, going to calculate it, and talk about how the different states of matter affect the density of the material. Then we're going to talk, like I said, heat transfer. Heat transfer is the main part of this unit, so we'll talk about the three processes of heat transfer. We'll then describe and explain how heat loss can be reduced from a home. And then we're going to talk about payback time, how we calculate it, how we use it. Pretty much of all the topics you cover in GCSE Physics, probably Unit 2, the last one, and this one are probably the most useful going forwards. Understanding how we generate electricity and how we get different forms of energy to make into our electricity. And then this one, to talk about insulation. These are decisions people are going to have to make in everyday life. Okay, again, some useful links, going through the different practicals, going through density and the different ways heat is transferred. Again, don't forget Seneca, go back to Unit 1, the link is on that presentation there. Okay, so density. Now, density, if you look it up, density is how much mass is in a given volume. The more dense an object is, the more mass the object will have in a given volume. So if you ever get a chance, we've got in school some kilogram blocks, and look at the size difference between the aluminium one and the brass one and the steel one, you very quickly realise that the density of aluminium is a lot lower than that of steel and that of brass. And the density is linked to how closely packed the material's particles are. The more of the particles we can get close in together, the more dense the material is. Because generally most of the particles, their masses are very, very similar. And what affects the overall density of a thing is how close we can get those things together. Now, solids will be denser than liquids, and they're denser than gases generally. There is one exception, and that is water. Water at around minus, I think it's -3, -4, is actually at its most, is actually less dense than liquid water, which is why ice floats. But that's an oddity. The rest, solids generally denser than liquids, which are denser than gases, and it's because if you think about the particles, how the particles are spread out. So in a solid, we have our organised rows really close together, and there is very little space between the particles. In a liquid, there's still very little space between the particles, but they are slightly spread out, and they can start to move around each other. And in a gas, large gaps. Gases, particles themselves move apart. Now, key thing to remember here, and this is a common mistake students make, is they don't talk about the gaps between the particles. They talk about the particles. If you look at my three pictures, the solid, liquid and gas particles are all the same size. You know, take our example, I was talking about water again. Water molecules themselves don't get any bigger when you heat them up. What happens is they just take up more room. Which you might think, hang on a minute, that's the same thing. No. So, think about on a dance floor, If you've got lots of people stood still, you can pack people in. However, once we get those people moving around, they themselves have got no bigger, but because they're moving around, they effectively take up more space. Alright, and that's the key thing to remember, that because the particles move around more, they take up more space rather than the particles themselves getting bigger. Okay, now you need to know how to measure density. To do that, you need to know two things about an object. You need to know its mass, and you need to know its volume. Now, mass is dead easy. Use a balance to measure mass. Okay, top hand balance is the most common type, and use them to measure the mass. And it's generally the first thing we'll do before we do anything else. Measure the mass of the object. Now, if it's a regular shape, for example, a cube, cuboid, sphere, where we can measure the thing, measure its dimensions. You can just measure those dimensions, use the appropriate volume formula. However, most of the objects we'll deal with are irregular, so we use what we call a displacement method. There's a couple of ways of doing this. I know in my school, or in our school, when we do it, we use the Eureka cans, which have a spout to collect water. More common way, we'll show you in a minute, but yeah, the formula, so like we said, it's the mass for a given volume. So it's mass per volume. Density is mass divided by volume. In the units, mass divided by volume, grams per centimetres cubed. So, this method, using the displacement method, what we do is we take a measuring cylinder. We make sure it's a measuring cylinder that is big enough to get our object in. And what we do is we fill it up to a certain amount of liquid. So in this case, it's a 250 measuring cylinder, and we filled it up to 100 to start off with. In fact, sorry, 150. We then carefully place our object in. If we throw our object in, you might lose water out. Carefully place the object in, and then we look at how much the water's gone up. So in this case, it's gone up to 180 millilitres. And the difference between those two, the displacement, the difference between the two, that is the volume of our object. So in this case, 30 centimetres cubed. Alright, so that's an important way. You can talk about the Eureka can method. The Eureka can method is where you would fill a beaker up to the very top, and then you would place your object in, collect any water that spills out, and then you would measure the volume of the water that has spilt out. However, this, using the measuring cylinder, is a lot better method to do. Okay, so heat transfer. Important thing to remember about heat transfer. Heat is an energy, and it's a concept really. It's not a thing. But heat energy flows always from hot things to cold things, never the other way around. So it will always flow from the hotter object to the colder object. And it's important in quite a lot of questions for you to realise which is the hotter object. You know, if you're talking about a house being insulated, generally it's the house that's hotter than the outside. If you're talking about someone wearing a coat, the body is going to be warmer than the outside. If you're talking about maybe a fridge, well, the insulation will be working the opposite way. The fridge will be cooler than the outside. So it's important to remember and try and picture which way the heat is flowing. Said that one. Now, there are three ways we talk about heat transfer: conduction, convection and radiation. And in the next few slides, we're going to go through these in more detail.
Okay, so conduction then. Now, conduction is our first mode of heat transfer we're going to discuss, and conduction is heat transfer by collision. So this is where the particles in the material have to physically collide to pass on the heat energy. Now, this is really the only way heat can actually transfer through a solid object. Basically, because those particles can't move very much, all they can do is collide. This is the way that heat is transferred through solids. Now, metals generally are good conductors of heat because of their structure. So they've got a lattice of ions, which basically just means, if we look at this diagram, the red dots here are the metal ions, that they are in a very regular structure. And because they're in this regular structure, they pass on the collisions really, really quickly. But the other thing that makes metals excellent conductors is their free electrons. Now, these free electrons can move around the substance, move around the structure. These are the blue dots in this diagram, and they pass on the heat via collisions. Again, making the whole object heat up far quicker. Okay, convection. So when a fluid is heated, its molecules will gain energy. This means then they move around more vigorously or move around more. And like we discussed already, when they move around more, it means the molecules themselves are going to take up more space. This means that that area of the fluid that's been heated is going to increase in volume. We've still got the same mass in a bigger volume, so its density decreases. Now, when we have a less dense thing, generally it will float on more dense stuff. So basically, this less dense pocket of the fluid will rise up and float on top of the more dense fluid, which is going to sink down to take its place. Alright, and what we will get is, as you can see in this diagram, this section gets heated, rises up. As it rises up, it loses heat to the molecules around it. And then this one, this is the more dense, getting dragged back down. Well, this is going to then take its place, and you end up with what we call a convection current. And this will keep going and keep going and keep going until all of the fluid is heated in the same temperature. Because remember, once something is the same temperature, no more heat can flow in or out. This is why, if you ever noticed, if you have a car that has sort of auto heating in it, what it will do is when it's heating the car, it will blow the air in at the bottom. When it's trying to cool the car, it will blow the air in at the top. Basically, because that's the same idea. If you want to cool something down, you're going to supply the cooling energy to the top, where the fluid will be the hottest. If you want to warm it up, you supply it to the bottom. Radiation then. So all objects will emit electromagnetic radiation. This is our third and final heat transfer process. And this involves the emission of electromagnetic waves. Now, the wavelength or the frequency of which an object emits depends on their temperature. So most everyday objects we deal with, they actually emit in the infrared region. And we are designed to detect infrared radiation of specific wavelengths as heat. Now, the surface of an object affects the intensity of this radiation. Alright, so if you've got a black or a matte object, these will emit and absorb radiation the quickest. Okay, so black matte objects will, if they are cooler than the surroundings, heat up quicker, or if they're hotter than the surroundings, cool down faster. Whereas the opposite, shiny and white, they are the best reflectors. This is why, if you notice in hot countries, their buildings generally are painted white, to reflect a lot of the sun's heat radiation away. Why black cars generally are hotter than white cars. Why, if you look at objects that are designed to either absorb heat or emit heat, they are generally black or a dark colour. If it is something that's designed to radiate heat, to reflect heat, yeah, we paint it white, we paint it silver. Yeah, we said that one. Alright, now, the other thing that affects all heat transfer processes is surface area. The larger the surface area of an object, the faster it's going to transfer heat, because it's the surface area, or it's the surface of an object where the heat transfer is going to take place. So this is why, for example, if you look at a radiator, radiators have lots of small fins. If you look at heat sinks, lots of fins. This is trying to increase their surface area to increase heat transfer. Conversely, if you're trying to stay warm and reduce your heat transfer, what you will do is make your surface area as small as possible. You'll try and huddle up and try and reduce that surface area. Okay, now just quickly, we spoke about the change in temperatures. Just wanted to show you these two graphs. So the left hand side graph is about cooling. So this is where our object starts at a high temperature and cools down. Now, key things are labelled on this graph. Questions that can get asked: starting temperature. Final question that can get asked, or another question that can ask, is what's the room temperature? Now, the objects can get no colder than the room they are in. Once they're at the same, remember, once at the same temperature as the room, we get no more heat transfer. So that's important. Likewise, if we have a heating of an object, we've already said our dull black surface is going to increase quicker. Now, both of these graphs are assuming things like surface area is kept the same. They're assuming that things like lids, they've both got lids, that they are made of the same material. So we're not affecting, or the conduction and convection are not affecting our results here, and that's important. Okay, so on to insulation then. So we spoke about the different ways heat can be transferred. So what about how we reduce it? Now, it's important. Reduce here is in bold and capital letters, because this is an important word. Not stop. We cannot stop heat transfer, but we can reduce it. Alright, so we design our insulation to reduce it. Now, the vast majority of insulation works by trapping air. Alright, the reason we trap air is because it's a poor conductor of heat. Okay, it's a gas. Remember, conduction relies on molecules colliding. Gas molecules far and far apart. Their collisions there are few and far between. The other thing about trapping the air, it's all well and good, we could just fill stuff with air and it would reduce conduction. But the problem we would have is that if we have free moving air, you can get convection currents and you can lose heat that way. So if we trap the air, it means we're going to get small convection currents and they don't tend to form very well. So trapped air doesn't form large convection currents. Quite often on insulation you'll see that it has a silver backing. Alright, that silver there is to reflect the radiation back into the object. Now a lot of people here get confused. When they see the word silver, they think of silver metal. Generally though, it would be like a shiny plastic probably. Alright, because we don't want the metal. Metal would increase conduction. So even if it is a very thin layer of metal, we're not going to get conduction through it. So see silver, think about reflecting radiation, not metal conduction. Okay, so this is on stuff when I was saying about this being useful for you in everyday life. So looking here at specific examples of insulations that you kind of need to know how they work. Alright, so if you think about it, roof insulation is pretty much like I just said, it's trapped air, it's big, it's fluffy, lots of trapped air. So that goes on to the one I said before. Now double glazing, okay, 2 layers of glass can have air in between them, can have nothing in between them depending on the price of the double glazing. Generally there'll be some sort of air, some sort of gas trapped in between them. Okay, again, trapped air, conduction, convection. Cavity walls. Now, cavity walls by themselves, that just means that what you have is you have your outside brick and your inside brick and then an air gap in here. So this would be air in between them. Alright, great. Air, we lose conduction. But we will get convection, that we will get this air moving around. So we would still lose some by convection. So what people now do is have cavity wall insulation. Okay, so now they fill the gap between the 2 layers of brick with an insulation. Again, trapped air. Quite often we'll have a silver side as well to reflect the heat back into the house that's lost by radiation. Okay, so we improvements, we lose convection over just having a cavity wall. Then we're talking about draft excluders. Alright, so draft excluders basically just make sure that you don't have air passing around the gaps in a door or window. Alright, this stops warm air getting out, cold air getting in. Now, all of this together will cost money to install, but it will save money on bills. And that's our next slide. Yeah, so why do we insulate? We insulate because it reduces our energy consumption. Okay, in the UK we're talking about here, we insulate because generally our homes are warmer than the air around them. So we need to spend less money on energy to heat our homes. Okay, if we're using less energy, obviously there's an environmental impact. Yeah, if we're using less energy, we need less power stations. Less power stations means we reduce the CO2 we emit. If we're using less energy, we're going to save money on our bills as well. Alright, and this leads to the concept of something called payback time. So payback time is the time it takes for the bills to equal the cost installation cost, sorry, the reduction in the bills. So the money you save equals to installation costs, and we calculate it using this formula. So payback time is the cost to install divided by the annual savings, and obviously this then would give us payback time in years. Yeah, if we had monthly savings, it would give us payback time in months. Now, there's a few things that affect this, and I think they're on the next slide. And so they are. So, payback time. Let's talk about it in detail, because this is one of the concepts, again, in exams, a lot of students get wrong. They see, oh, bills are going up, that means that payback time will increase. No, let's think about this carefully. So, we'll talk about environmental conditions to begin with. So environmental conditions do affect payback time. If you have a warmer winter, that means that you're not going to lose as much heat out of the house. If you're not losing as much heat out of the house, you're not going to need to put your heating on for as long. And if your heating's not on for as long, you're not going to spend as much money on your electricity, and that section of electricity or gas that you've saved by having good insulation is going to be worth less. So you save less money, which will increase your payback time. Now, the other thing that has a big impact on payback time is utility prices, is how much the gas and electricity costs in the first place. So if you have a higher price for gas and electricity, increasing your bills, this means that the saving amount is now worth more. Yeah, so if I've saved 10 units of electricity or 10 units of gas, that saving will be worth more if my bill is more. And that means that this is going to reduce our payback time, because our annual savings, the bit on the bottom of the equation, is now bigger. We still paid the same to install it. The bit on the bottom is bigger. We get a lower payback time, and that's something students seem to forget. All right, if we're paying more for gas and electricity, we end up saving more, which you might think, hang on a minute, how does that work? Well, the stuff you're not using is now worth more, so that's why you're saving more, and that will reduce your payback time. Okay, key real world data. Yeah, because this is a topic that exists in the real world, the exam will love finding obscure data, and they're very proud of it when they find like real world data that they can actually use in a question. And that causes some students havoc because they go, oh, we've not learnt this. Well, you have, and you will have, or you should have. What you may not have learnt is all the specific examples, but you should have the skills to look at a graph and analyse it. There's some important things to remember. The vast majority of the UK's power still comes from fossil fuels. Now, it mainly now comes from gas. Over the last 20, 30 years, the amount of coal we've used in the UK has gradually reduced, and the amount of gas has increased really to replace the coal. Okay, now what that means is, because we mainly use fossil fuels, any change in the amount of electricity needed has a massive impact on our greenhouse gas emissions, on our CO2 emissions in the UK. Alright, now the other thing to remember is some questions I've seen asked on this, they start talking about like petrol cars versus electric cars. Now obviously petrol cars are going to release CO2 when they're driving around. Electric cars don't. But where does our electricity come from? Yeah, driving an electric car might well reduce the CO2 emissions from the roads, but you're going to increase electricity usage, therefore increase CO2 emissions from power stations. So there's a bit of a trade-off there. So it's important that you keep a sort of whole world view on this, and that you remember that the question might just be talking about power station data, but it doesn't include things like factories, or doesn't include cars, doesn't include agriculture, all of these other things that release CO2 as well. And that's important to remember. Remember the whole world, the different things that release CO2 all tie in together. Okay, so over to you. Like I said before, click the link in the description below if you're watching this on YouTube. If you've got the PowerPoint version of this, stop the slideshow after this thing, and if you click on that document, it should download the PDF for you to have a go at the questions. Alright, hi guys, so we're going through these questions then. Hopefully you've downloaded them on from the previous slide. Okay, so first question then, all of these are about heat transfer. Now they may include some other bits and pieces, just because of the way the questions work, but we'll cover them when we get there. So we've got a pie chart here, so we've got a bit of information at the top, important to read that, but then we've got a pie chart talking about different ways that energy is lost. Okay, use the information below to complete the labelling on the pie chart. One label has already been done. So we've got the percentage of energy lost to the walls is the greatest. Windows and drafts have equal percentage losses. Windows and floor percentage losses add up to equal the percentage loss to the roof. Okay, so we're told that drafts is 15%. Now we're also told that windows and drafts have equal percentage losses. Okay, so that means that the 15% above the windows, above the drafts is also going to be windows. Alright, so what we got left now? So we've got left floors, walls and roof. Now it says the energy loss to the walls is the greatest, so the number that's the biggest is 35%, so that's going to be walls. Okay, so we're now left with floors and roof. Okay, so windows and floors add up to equal the percentage loss to the roof. Okay, so we've got windows and floors add up to equal percentage loss to the roof. So the roof must be bigger than those two, so that makes it 25, which makes the floor the 10. And check, 15 plus 10 is 25. Okay, so the second part, to reduce the energy loss through the roof, the scheme suggests installation of fiberglass insulation in the loft. Explain how it reduces energy lost by convection. Okay, so first thing, whenever I see energy, ever see like fiberglass or talking about insulation, first thing I'm going to write is that the insulation traps air. Okay, so that's the first thing I'm always going to write. In fact, there's only one P in trap. Alright, so insulation traps air. That's always the first thing I'm going to write. Now, we're talking about convection. So how does trapped air reduce convection? We're not going to get convection current. So this stops convection currents forming. So we could read the whole forming. Hang on, forming. Okay, so that's how we go with that one. We've gone down too far. Okay, so strict regulations, minimum thickness, you can see there. So we've got a graph. Using information from the graph, tick 3 correct statements. The 3 statements we're going to tick. So what have we got? Every 5 years, the required thickness of insulation increases. Well, that's not strictly true. If you look, you know, these are 5-year gaps, and it seems to be not every 5 years, so that's no good. The required thickness of loft insulation in 2000 is 8 times thicker than 1970. So 2000 is around 200. 1970 is around 25, so that's fine, so we'll tick that one. 1960s houses did not lose energy through their roof. Well, that's wrong, because they had no requirement for insulation. A house built in the 1980s needed 210 millimeters of loft insulation to be added to bring it up to 2015 standards. So 2015 is 250, 260, 270. And 1980 was 60. So yes, that's a difference of 210. So we'll tick that one. The general trend on the graph indicates that the required thickness of loft insulation has increased at an increasing rate. So we want to try and draw like a line of best fit across here. Yeah. Alright, yeah, if you look, this is a curve going upwards. So yes, we'll tick that one. The required thickness of loft insulation will remain constant after 2015. Now we don't know that because there's no other information past 2015 on this graph. Okay, so a homeowner must install new in extra insulation. The loft has an area of 120 meters squared, and it must be at least 270 millimeters to meet new building regulations. Here is a selection of fiberglass installations available. Calculate the payback time if insulation 3 was installed in the 120 millimeter extension. Okay, so payback time is going to always be, our payback time, I'm going to call that PBT, is always going to be, I don't think you can see that, can you? No, right, okay, we'll bring that down a bit. So our payback time is always going to be the cost over the savings. Now here, the cost is going to be 4.5 times 120, so it's 4.5 pounds per metre squared, divided by, times by the 120 square metres of the roof. Now the estimated saving per year is 98. Okay, and that doesn't need timesing by 120 because that's just each bit gives us a saving of 98. So we then do that sum, 4.5 times 120, 4.5 times 120 divided by 98, and that gives us a payback time of 5.5 years. Okay, so the next question here. Homeowner considers installing insulation 1 as it's cheaper, but the builder says insulation 2 should be installed as it will save more money over the 40 years. Explain which, with calculations, whether the builder is correct. Okay, so it will save more money over the 40 years. Alright, so this calculation, so we've got to do a few calculations here. What we're going to do is we're going to calculate the difference in cost between the two, and then how much they're going to save you in the 40 years and do the difference. So if we look at insulation 1, that's going to be 3.5 times 120, take away 84, take away 84 times how long? 40 years. So that gives us 3.5 times 120, take away 84 times 40. That gives us a saving of money of 2,940. So that's the negative number, means that that's a saving. Yes, that's minus number. We've said the money we're paying out is positive, taking off what it saves us. So we've got a 2,940 saving from that one. And for number 2, we do exactly the same calculation here. So that's going to be 5.55 times 120 minus 111 times 40, and that equals 5.55 times 120 minus 111 times 40. That gives us a saving of minus 3,007, or a saving of 3,740. So builder is correct. Now, it's important that you write that bit down, so builder is correct. Because if you don't, what's going to happen is you're going to lose the second mark. Alright, you're going to lose that second mark because ultimately that's the exam board wants to see you drawing those conclusions. Okay, so this question. So this is one of the, these are 2 of the 3 specified practicals when it comes to doing conduction, convection, radiation. So this is something that, whilst perhaps not covered in the PowerPoint, it's here in these questions for us to go through now. So we've got potassium permanganate crystals, lovely purple coloured crystal that when you put them in water they slowly dissolve. When you heat the water up they enable us to see the convection current. So explain why the coloured water moves in the way described above. So what you see is that you see when the water is heated, you get a clockwise convection current. Alright, 2 marks. They're going to want you to talk about going up and coming back down. Okay, so why does the coloured water move in the way it does? So as the water is heated, it becomes less dense. Now this is explain. Yeah, that should be alright. It becomes less dense. Alright. This less dense water floats up and cools, becoming more dense. So it sinks down. Creating the current. So you basically got to explain why it rises up, because it becomes less dense as it heated up. The second mark is then for saying, well, because when it cools, it's going to become more dense and it's going to sink back down. Okay, so they conduct an experiment using the 3 metal rods. See all that, or 4 metal rods before we got those results. Now, this is a classic case. Most questions say radium contains information. This is one where pretty much the rest of the question is complete and utter rubbish, because it says explain in details the process of conduction in copper in terms of the motion of its particles. Alright, so the rest of the question here is irrelevant. You don't actually need to read anything else. We're just talking about conduction in copper. Now, copper is a metal. Alright, so we can write that down. That will probably give us a mark. So copper is a metal. Good place to start. Let's have metal. Okay, now metal then. So metal structure. Metal structure. Metals have a tight lattice of, well, we'll call them atoms. Atoms will do. It's probably ions, but atoms will do. This means as one end of the copper is heated, the vibrations are quickly passed through the structure. Now the other thing you've got to remember is we said particles, so we've said about that. What else do metals have? Metals have their free electrons. It also has free electrons which can pass through the structure, passing on the heat. And that's pretty much what you need to write for your 6 marks. Okay, on to the next question then. Classroom has a volume of 80 meters squared, contains 104 kilograms of air. I'm going to try and calculate density. So density is mass over volume. So it's going to be 104. Let's get it right. Around 104 divided by 80. 104 divided by 80. 1.3. Now we want the units as well. Kilograms per meter cubed, because we've done kilograms divided by meters cubed. That's what we need for 3 marks there. Okay, the classroom is now heated by a radiator. Set up convection current in the air, at which point A, B or C is the classroom the hottest. That's going to be A. Hot air rises. The top of the classroom is always going to be the hottest bit. So that's going to be A. At which point A, B or C is the classroom least dense. Well, the least dense is always going to rise to the top. So that's also A. No, give a reason to your answer. The least dense air is always going to float up on the more dense air. Okay, so another classic QWC question here. Loads of students, when they answered this or attempted this, started talking about, oh, they see silver, so think metal. Start talking about metal. This is what I was going on about when people see silver, talk about metal. No, this is plastic. Although it's silver coated, we're talking about the plastic here. So we've got shiny silver plastic bubble wrap placed on the wall behind a radiator. Explain how this can reduce heat loss from the classroom by conduction, convection and radiation. Now, for me, if I'm going to answer a question like this, I am probably just going to put in 3 headings: conduction, convection, radiation. I'm going to talk about each one. So let's start with conduction. So how does this reduce heat transfer by conduction? Well, if you think about it, it's got trapped air. Okay, so we're going to write that down. Trapped air is a poor conductor. This reduces conduction through to the wall. Yeah, so we put this on the wall. So the air between the radiator wall, the air in this gap here, pardon me, is still going to conduct a little bit, but by putting this trapped air here, we're adding another layer that's going to hopefully stop that conduction. Okay, our next thing we're going to have is convection. So, how does this reduce convection? Well, we've got trapped air. So no convection currents. So what we don't get is convection currents behind the radiator passing the heat through. Okay, and then radiation. Well, radiation here hopefully is the simplest. Alright, the silver reflects the heat back into the room. Simple as that. That's what you're going to write. Okay, thanks for watching this video. Well done for making it through right the way to the end as well. If you liked it, click like. If you got any comments about stuff that's missing, any improvements, anything you didn't understand, leave them in the comments below. If you look around me, there should now be the playlist for all of these videos, along with YouTube's algorithm recommended one of our other videos that you should go and watch. Also, don't forget to subscribe to the channel, follow us on Twitter, link in the description, just to see the other sort of stuff that we produce.